I finally.
With literally anything. Okay, let's get started. Welcome to Cyber Lab. Let's give it up real quick. Welcome everyone. We have an exciting day planned for everyone. Let's jump right into it. Okay, a couple announcements. Next week we are kind of off for cyber. We don't have any Cyber Academy or Cyber Lab plan, but if you do want to hang out with us, you're like, man, I just want to come study with you guys, hang out. We do have a couple socials. So next week, same time, same place, this location. We have a couple study socials. So if you want to come here, hang out, do some studying, we'll be here. So come hang out with us. It's very chill. Get some help from people on exams and stuff like that. This Saturday we have our first social of the quarter where we're going to Santa Monica Beach. So that's this Saturday. If you'd like to come, meet at Sproul Turnaround at 11:45 a.m. The bus comes at 12, I think, so make sure to show up on time. Don't forget your tap card. That's free. Go to the Central Ticket Office and grab that. PBR, this is a new announcement that I forgot to mention on Monday. We'll be having another CTF, so I put out a vote, and you guys were like, let's do week 5 CTF, so we're going to do week 5 CTF. So this will be the weekend after week 5, so this is the Saturday after week 5. Same time, same place. We'll be doing Lake CTF, which is a pretty good CTF run by this CTF team, Polyglots. So definitely come pull up if you want to sort of.
It's the 21st of October.
No, the date's wrong.
Sorry, the date is wrong, but it's not this Saturday. It's next Saturday.
Saturday, got it.
All right. Show of hands, does anyone need to fill this out? I feel like this will be the last time I need to ask it.
I filled it out, right? Yeah, you made me fill it out.
Okay, great. If anyone needs it, let me know. All right, but without further ado, we have a very interesting talk by a very cool person, Anderson. He's gonna be talking about this really interesting hardware side channel called Starbleed. So, please give it up for Anderson. Let's hear what it's about.
Okay, so I'm Anderson. I'm a third-year computer engineering major. Last summer, I worked at the Aerospace Corporation, working to implement this Starbleed vulnerability. Okay, so Starbleed itself is it's a vulnerability on Xilinx series or Xilinx 7 series FPGAs, and it was first documented in 2020, so pretty recently, and it essentially allows you to leak encrypted designs on the FPGA remotely through some debugging interface, and all you need is like some sort of access to these debugging interfaces. So there's some the authors if you want to see them. They're like German.
Savannah already has a question.
Could you explain what the FPGA is?
Oh yeah, I'm going to yeah.
Oh, okay.
So first, what is an FPGA? So if you take it M150, M152A, if you know how painful it is, but it's essentially, or it's called a field programmable gate array, or FPGA. So it's basically a reprogrammable digital circuit that's on a on some ASIC or chip. And the main benefit of this is that you can basically design any sort of hardware architecture to sort of accelerate whatever software application you want to do. So compared to a regular ASIC, like a CPU, which can pump out one particular operation at a time, you can design you can create certain hardware designs on an FPGA to utilize more parallelism. So if you want to perform a lot of vector operations, you can sort of create your design that way. And it's pretty it's used pretty often in the military, aerospace, cloud acceleration, and high frequency trading industries, which is it's a really niche field. But so you can mainly just create these designs using low level RTL languages like Verilog and VHDL, or you can also design these low level designs using C++ through a technology called high level synthesis. And after you can compile and synthesize these designs that you create in these languages into certain bit streams that you upload to the specific device. Wait, I have the device right here. It does $100 or something. That's cheap. Yeah. but this is like a pretty small FPGA, but you would basically like just plug it in and program the device that way. And a really cool part is that if you have some sort of IP that you designed and you don't want anyone like, like entering some Trojan into it, you can encrypt the design and yeah, no one can, yeah, ideally no one can leak your design, but as you'll see with Starbleed, that's a big issue. So within these FPGAs themselves, there are sort of three vulnerabilities. First, as you upload in encrypted design, there's a pretty weak encryption scheme itself, but this isn't like a really big problem. But this like problem is like coupled with some of the other vulnerabilities, makes it pretty bad. There's a scheme that also validates whatever commands are in the bit stream after it executes. So it runs all the commands first and then checks if the commands are valid. And for the third vulnerability, there's sort of there's like a channel that can store information even after a validation failure. So you can store information there after leaking some information. So we'll talk about AES CBC mode. So yeah. AES CBC mode or cipher block chaining is it's a sort of cryptography. I'm not too familiar with like crypto stuff, but this is how the FPGA encrypts and decrypts its bit stream. So basically with like AES AES encryption, it has separates into different blocks. So it's a block cipher and or separates the bit stream into these different blocks. And with the cipher block chaining mode, it XORs the after encrypting, like let's say the first block with after you provide like some initialization, it XORs this cipher block or this the encrypted block to the plain text of the next block over. So you can essentially yeah, so this is during the encryption, and the decryption is basically just like reversing the entire thing. But if you know what this what sort of changes you want to modify to this block, for instance, you can simply provide some sort of offset here, and this offset will be XORed onto the plain text over here. So you can arbitrarily modify any word within the bit stream and sort of craft your own designs if you know what this original plain text is. So that proved pretty like useful later. So next one is they're like used before validation for HMAC authentication of the bit stream. So HMAC is used to or HMAC creates like a tag that essentially authenticates the bit stream to see whether it's been changed or not. And typically they would validate the HMAC or the MAC itself beforehand, or the MAC is should I explain? Or the MAC is like a message authentication code. It's you basically produce like a tag based on the entire like sort of data that you want to encrypt, and or like not encrypt, but like you want to keep the integrity of it, and yeah, it would validate like usually beforehand after before running it. But the way the FPGAs work is that they first run all the commands first, because as the bit stream is being decrypted by the engine on the FPGA, it just runs it in like a FIFO fashion, or first in, first out. And after the entire, all the commands are run, at the very end, do we have the HMAC tag. So it only validates at the very end after running all these commands. And then if the bit stream is somehow like modified maliciously, then it just fails and resets the entire FPGA. So this would be a pretty big problem if just for like running like basic commands, but we aren't really able to persist these changes after it resets. But then comes like sort of the third vulnerability, where we have a boot persistent register. So after the FPGA resets, there is a particular register like documented directly in the Xilinx documentation that stores any 32-bit word between resets. So after we modify this bit stream arbitrarily using that AES CBC mode, and the HMAC fails at the very end, we can write this any specific word within the bit stream to this register. It's called WB star, or warm boot start, and the FPGA will reset, but then the specific word that you wrote to that register will still stay there even after failure. So you can simply like read out the bit stream out of the after modifying some command. So yeah, so here's like the entire steps. I know it's like all these like vulnerabilities are kind of confusing, but in like sort of like a step-by-step path. First, you within the actual bit stream itself. So let's say this is the design that you synthesized into a bit stream, and so we know the specific locations of certain commands, like the command write WB star. It's in this like specific offset from the start, and we first want to find this command, right? And using AES-CVC mode, we simply provide that XORed offset onto the previous AES block. And then this offset right here, let's say like in hex like C, would be applied onto the next block simply by XORing our previous block, previous encrypted block. And after doing this, we would change, or we could apply like an offset to point to any like address. Let's say this offset right here points to this word. And after this word is decrypted, it would be written to that particular register using this command. So after we modify this bit stream, we simply program the FPGA with this design, and then it would obviously fail its authentication because you modified the bit stream, but the data itself that was decrypted and written to the register would not be changed because it would just persist through that failure. And then after doing that, you would simply craft your own other bit stream that just reads from that register, and you're able to leak any particular word within the bit stream that, or any decrypted word within the bit stream. So yeah, just keep repeating this for every 32-bit word, like a gigantic design, which might take like a few hours, but. So here's like sort of how it would work visually. So like here would be like the decryption engine. You modify your word right here, and then it passes it through here, and then as it passes it through the or is decrypted, it executes the commands in like a FIFO fashion. And then within the FPGA itself, after decrypting the design, you would write the word to WB star here. And then the HVAC would somehow fail. And then you would just like read that specific configuration register. So Xilinx's response, the manufacturer of these FPGAs, they basically said that this type of attack is very similar to DPA attacks or differential power analysis attacks, essentially measuring like the power traces of the device itself. And therefore, it doesn't weaken the security of the device, which I think is a really bad response because it's like these devices are already vulnerable, so it doesn't make them more vulnerable. And like the only solution is contact your compute application engineer. So yeah. It's really bad. They're not going to fix it anytime soon. And these are like some of the most common FPGAs in the industry right now. Aside from like SoCs, like they're combined with like a coprocessor. Yeah. So I have like a demo video. It's kind of boring, but it's just like running a script. It's quality kind of. It's Joker.
The max.
Okay. So first we just here's the design right here. It's simply assigning like one of the onboard LEDs to like a 1-bit, but like we don't need to know what the design is. So first we program the FPGA with a certain key. I just put all zeros just for like. So this programs the AES key into the block RAM of the FPGA. So if you were to like reset the FPGA, the key might, I don't think it's like it doesn't persist after like resetting the entire thing, or it's not in the fuses at least. Okay. Right, so I just like open. Okay, so I have the particular design right here that I synthesized, and I just like built modified like an open source tool for debugging FPGAs itself. That's called OpenOCD. And here we're just like performing the attack. So every single line is or up to like I think 200 lines is being decrypted right now. I think that's like. Okay, yeah, it's pretty boring, but that's basically the entire attack. But I'll show you what the output is on sharing screen. And I'll show you what the so this is the original bitstream design, right? And wait a second. Okay, but the visual I showed earlier, right here, you can see that right WB start of the encrypted section is the HMAC. So you would have the original HMAC key. Ideally, this would be all like zeros, and then you have the iPad of the HMAC operation, and then this basically tells you when the encryption starts and the length of the encrypted section. So we can look for that particular word. So over here, so you can see here, it's the specific word up here. And this tells you the length of the bitstream. And here's the start of the entire encrypted section. You can see it's like random. But after performing the attack, we have another bitstream file. So this kind of ignores the initial header. We don't really need the header information, but it essentially started decrypting the bitstream from the start of that original HMAC. The starting HMAC. So like we see here, we start right at this line. So the original key was all zeros, but for this we XOR the iPad, which is these specific bytes with all the zeros. That's why they're all the same. And there's like some random bits right here from the previous block. But we can see here that I think this is the right WB star word. And this is the so we essentially decrypt this entire section, this entire design. And it's a pretty small design, so it doesn't go any further than down here. But yeah, so now we know that this design is like, if you know how to read this bitstream, then it's just writing to the LED. But performing this attack on the entire bitstream for this device takes around 5 hours, which is really bad. There isn't like any better way unless, because you basically have to cycle and like reset the FPGA for every 32 bits, which really sucks. But yeah, on like bigger devices, it can be like take a whole day. That's the attack. You want to swap?
But yeah, any questions for Anderson?
I know this might be a little like fringe too. It's like it's a very small field, I guess.
Wait, so sorry, any questions for Anderson or? Yeah.
So I guess your job in the company kind of, so did the company already know about this issue when?
Yeah, so it was already there's our like kind of an advisory, but they wanted to see what the like how much it will cause like a threat to their current system. So the aerospace industry uses I think it's called SpaceWire for their communication protocol, and ideally they wouldn't want someone to like insert a hardware Trojan into that design. So through this way, there's actually a second attack that builds on top of this, where you can forge HMAC tags and be able to modify the bitstream, like, and then have it not fail on you. So I was sort of like kind of advising them on that, but yeah.
I think I thought I saw another hand in the back, or did anyone want to? Oh, it did. Oh, yeah. Sorry, can you speak up?
Discover new hardware vulnerabilities.
You want to add?
I didn't discover this vulnerability, but there's like this it was like originally the paper from what university? It's like one of the somewhere in Germany. Yeah. One of the that's always nice. Yeah.
Like there's like this one.
Yeah.
A lot of research.
Yeah.
I'll also add that there's this interesting paper that came out recently by Project Zero, I think, about like this interesting ISA vulnerability called Zenbleed. There's a very interesting live overflow video where he explains how you do hardware fuzzing, which is very weird, but very cool. So it's like you, instead of like, if you know fuzzing, normally you test when the program crashes, but obviously it's hardware. You know, what is a hardware crash? Well, if you take like, EC116C, there are special registers for debugging and things like that. So flipping values in those registers sometimes are indicators that you cause an interesting fuzz result. So, any other questions for Anderson? I have a quick question actually. So, could you explain your threat model a little bit here? Because I didn't fully understand.
Threat model?
Yeah.
I wasn't exactly too sure. I think it's they just sort of gave me the task, but for the most part, it's probably the adversary could be some so let's say you have some cloud server, right? Since this can be performed remotely, ideally the attacker would have this like encrypted bitstream file. So they already have all the resources, but they don't have the exact like AES key to decrypt it. But they do have access to this like FPGA remotely somehow, and they can use that sort of as the oracle to like basically decrypt it for you.
Yeah.
How do you remotely get access to the FPGA's in order to?
Oh, like I think there's a lot of I haven't used it personally, but there's a lot of I think AWS is rolling out some like cloud FPGAs, but you definitely need access to debugging interfaces for any sort of development, right? So you just need access to like for here it's like an FTD like JTAG FTDI. There's something, yeah. But yeah.
Anyone else or? All right, let's give it up. Oh, to start.
Yeah. So basically, it doesn't really affect anybody who isn't like remotely hosting the FPGA, right? Because like, I guess the other option would be like, oh, you break into some like warehouse and you plug the computer into
Yeah.
the FPGA.
I mean, it doesn't have to be remote. If you have physical access, obviously you can get anything out of it, but yeah.
Any other questions? Oh, yeah, another question.
I mean, I don't know, it might be like a reach question, but like, what would you think would be like a possible fix? So I think it was lazy, so like, just.
So a good fix that I kind of proposed was you add some extra hardware in front of the debugging interfaces to perform that HMAC authentication beforehand. So it like reads through the entire bitstream, but that makes like debugging a lot worse because there's some extra latency in running, especially if it's some like remote FPGA somewhere. So aside from that, it doesn't really solve the problem of that like boot persistent register. It can still like leak information through that, and the device is directly on the silicon, so you can't really like patch it really easily because it's already within like the manufacturing. But Xilinx does have a new series called Ultra Scale that is not like susceptible to this. It's like a tiny bit susceptible, but like they're fixing it in newer versions, but these are still like pretty like common nowadays.
I don't know if you answered this before, like, but what kind of data would be posted on the FPGAs? Like, what type of data would be inside of it?
Oh, like it's like any sort of design or like company IP that you want to like kind of keep secret and like encrypt. So you can just like leak information through that. If like some rogue employee wants to take some information that they don't have like clearance for, it's already encrypted, they can on this pretty easily.
It was like if you remember the bitstream data, that's like a file version of like proprietary hardware design. So exfiltrating that is very bad because people lose a lot of money for proprietary hardware. So, all right. Any other questions?